running time?
No.
Okay. It's enough.
Okay, thank you.
Thank you also. Next.
So I have to show you lab number 2 with producer consumer. Here is the main function. So I create a new product producer consumer object, and I give it these 2 vectors. I chose now these ones because it's easy to compute them. So, okay. So, and I used some C# assets. I don't know if it was good. I tried to make my life easier. So I used this channel and these 2 tasks. One of them is the producer, one of them is the consumer. And they share this channel where so the producer puts the multiplication of the 2 items, of the 2 elements. And here the consumer is reading the multiplication and adds it to a global sum. And yep, and if I run it, so now it should show 3 because it's 1 + 1 and 2 + 1. Yeah, and I also can show the sums, like the intermediate steps. Yeah, it's 1 + 2 - 3. I can also try with the longer vectors if it's necessary. I tried just to see how it. Yeah.
Okay. Let's see a little bit more the code.
Yes.
Okay. So what's exactly the semantic of try write and try read?
So they put in this channel what they compute, and here the consumer is reading asynchronously what the producer wrote on the channel. Here.
And what about waiting and things like this? So what happens if I call try read and there's no data yet?
I think what happens is that it waits for the data to arrive, because it's wait to read asynchronous.
And what does the await do? The await keyword.
This is to I thought it was it is used with async here because I don't know. I tried to, yeah.
You have an async reader, so you have to await the result from that reader. I don't know what you do with it, but it's just there. So when you read a sync, you have to await it.
Yeah. Yeah, I used what C# gave me, so I think I should have looked more into what it does behind it as well, not just. Yeah.
I think there also should be a channel reader that doesn't read a thing, so you can get rid of the awaits, but I'm not sure.
The thing is, it's a more complex feature. I have to read the exact spec myself because I'm not familiar with exactly what is this doing. We'll talk a bit more about await because essentially a function on which you await is a function that returns a future object. And await actually tells the compiler to break the code into several pieces and to add continuations. So you write the code as if it were to execute on a single thread and call a function and wait for it to actually return a result. But what the compiler does is a lot of heavy lifting into breaking the code into pieces, and the pieces do not necessarily execute on the same thread. It's a very nice optimization, but I should read into the details, and it seems that it's not very nicely documented what exactly is each of the function doing. For instance, on try read, I have the documentation open in front of me, and it says attempts to read an item from the channel, and it returns the read item or a default value if none could be read. And the question that I have, and that I would have expected the documentation to answer me, is what happens if there is no data available at this particular point in the channel versus what happens if the channel is already closed and all the data has been read.
Mm-hmm. Yeah.
Because that was the issue of this lab, and the emphasis. You have the producer that produces objects and puts them in a queue. Now, it can be a queue of infinite size, so much larger than we could use. That's the simplest way. And then the producer just produces and puts there, and that's it, and notifies the consumer. But the consumer can always be faster than the producer. And in that case, it will have to wait for the producer somehow. And I'm not very sure how is this handled with the channel. Wait for read async. Okay, if you have a single consumer, you can have a function that waits until you have an element. But if you have multiple consumers, then such a function is a bit useless, because you can call it, say that it has an element available, and by the time you manage to actually ask for that element, another thread took it in front of you. So you need a function that does both operations atomically. You ask for an element, and it can return you the next element. It can tell you that there are no more elements and never will be any of them because the writers closed the queue. I suppose this is what happens in line 22. The producer tells that there are no more items to be put in the channel.
Yeah.
And it may be that the queue is empty, but there's no sign that there won't be more elements at a later time. And in that case, there are two possibilities. Either the function blocks, that's the easiest one to use, or it returns some kind of information that there's no element for the moment, and it's the responsibility of the consumer to do the waiting. Or here it's a third option. It returns a future that is to be used by the consumer. And indeed, this async await is very nice on here. And by the way, that's why you launch it with task factory start new, That's a thing that takes a function returning a future. That's why you put there a thing.
Yeah. Yeah,
So
I guess I shouldn't have ventured into advanced stuff without actually understanding, but yeah, I'm sorry. I try to be fast. Try to make
it's
myself.
okay for
Yeah.
It's okay for now. I'll take it as it is. But
Yeah.
indeed, it's a bit more advanced stuff here, and I'm not 100% familiar with. I don't have a 100% understanding actually of what is here now. But it's okay. Thank you.
Thank you.
Then please the next one.
Yes, I'm the next one.
Yes.
Okay, I'll present lab 3. Here.
By the way, you know that there is a famous person with your name.
Yes, and wrote a book about C++, I know. I'll have a hard time trying to surpass him.
Who knows?
Okay, let's hope for that. So here I have N and M for the matrices, 2 matrices, a number of threads, and okay, so here are the variables I'll use, which are all global. In the main function, so this is how I structure my program. I'll create always the same type of matrix, so I can have predictable results and check them at the end. I compute how much should each thread process with this formula, so all the cells divided by how many threads there are. And then I have the 3 cases, task by row, column, or k element. I'll show you first. I mean, I think they're all the same, but you'll see. So task by row, in which I pass the threads into process. And what this function does, it creates number of threads. In each thread will run the task by row. For this, I use a variable processed, in which I keep track of how much each thread, where we are at the processing stage. So the first one will process, let's say, the first 20 elements, the next thread, the next 20 elements, and so on. So when I create a thread, I pass to it where to start from and how much to process. As a side note, the last thread will process a bit more, just to make sure that it covers the whole matrix. In some cases. So a task row, so what each thread will do in this case, in this scenario, when we go row by row, is just the classic for loop, double for structure. I start from the given row, and the column starts either from 0 or from the column I'm given if I'm given something different from 0. And I'll also keep track of how much I process, so I know when to stop and return. And what happens at each step is I add in the result matrix, the multiplication, and this is the simple function that was required, just multiply 2 elements. And that's it. So that would be a task by row. Then I have a task by column, which is very similar, but I just switched the 2 for loops between them, and I added the exit case inside this loop. So that's very, very similar. And from k to k elements, I also pass in k, which is 4, I think. And what I do, I go by k elements, and I have an encoder-decoder structure. So I compute the current position. I mean, I have the current position where the thread is at. Then I compute the depth, so basically where it is. Let's say it starts from 0 and k is 4, so we should go to 0, 4, 8. In order to know which position is, let's say 4, if I'm at that 4, I have this get element position method. So I pass in like 4, and it will tell me where in the matrix is 4 or 8, going row by row, because that's how it was mentioned. If that makes any sense, the way I explained it, at least, because it does make sense, it works. So these will be the three tasks, the three different tasks, and the way I create the threads with the tasks is very similar, so I'm not going to go through them. They're almost the same. And the cherry on the cake would be the tests. I ran some tests in debug mode on x86 without the thread pool, and here let's see. So I have by row. On the left, on the column, I have columns. Okay, here I have the sizes, and here I have the number of threads. And what's interesting to observe is that if you increase the number of threads, the time decreases. For this one, for instance, when you have 10,000 by 10,000, and that makes sense because you have more threads to help you with your work. But if you do the same thing on the column, sure, the times decrease, but they take a lot longer than if you go row by row, which was also expected. And going by K to K elements, it just explodes. For some reason, I couldn't even go to 10,000 by 10,000, and the values are very, very huge. So this is the implementation without the thread pool. I'll move on if there are no questions at this point to the thread pool version.
Okay.
I use the same class you posted on the web page for the thread pool. I think no modifications, it was functional. And here I have the lab with the pool. 1 second, I'm not sure what I commented here. I think. So the main differences are in the main function. Instead of declaring the vector of threads, I create a thread pool, and I pass this thread pool to these functions that take care of running the tasks. And let's see one of them. So instead of creating number of threads, I enqueue in this thread pool this many tasks as I'm given. Now there is a difference between the number of threads and the number of tasks. Just to be more explicit, I have 5 threads and 500 tasks, for instance. And yeah, that's the only difference. So I just enqueue these rows, these tasks, and they function the same. So the tasks are not changed at all. The implementations and the results part, which is also interesting, follows the same structure as before, but instead of having number of threads here, I have number of tasks, and the number of threads is always 5. And what we can see here is how small the times are, even for a row or column. Maybe they are too small to even notice the differences between them. But it's obvious that this is a way better approach. So I think this was the conclusion of the lab, and I kind of got it.
Something is strange, however, in the data you got there. I'm a bit surprised by the last things because it shouldn't be such a small time.
Yes, I've had some problems. As you can see, after I close the thread pool, I have to wait 1 second to see the results. I'm not sure why it happened, because I print the matrix with the results, and if I don't wait a second, the matrix will be empty.
Does the close function wait until everything finishes?
No, it just notifies apparently all of them. Yeah, maybe this is the cause. So I have to wait for everything to finish, but how do I do that?
For instance, by destroying the thread pool or by modifying a bit the code.
Oh, so you mean, I could do this TP. I think. What's this? Let's see. So this is rows. 5 by 5. Okay. So initially this took 6 milliseconds or something like that. Yeah, it takes more now. So yeah, I have to recalculate the values now. It was strange.
That's a bit more realistic.
Yeah.
Because so it is faster with the thread pool if you have a large number of tasks, because you don't have the time spent in creating and destroying threads. But other than that, you should expect quite a long time for the operations because it's still n power 3. And 10,000 power 3 is 1,000 billion. And even at the rate of, let's say, 1 billion operations per second, it would be 20 minutes. So.
Okay, so I won't be testing this.
Probably not. Probably not.
Okay.
But it's good work, even if not complete. So from my perspective, I'm satisfied with that, and I'm sure you will see what happens next there. So it's enough for me for now.
Okay, thank you.
Thank you as well. Okay.
I started.
Yes.
This is lab 2. I have some classes again, one for the product consumer, one for the summation consumer. I call them both consumers because the product consumers take these vectors, but they're in the main method basically. I create them. Get the reference inside the product consumer. I get the reference of the summation consumer inside the product consumer, and I start them both. And then I join them. The join is a mechanism like the function is inside the class, but it's called in the main method. So this works the way I tested it. I hope it's good. And how do they look? The product consumer header and host, the conditional variable, and the mutex is this is to select the vectors. NQ and DQ are to put the results inside the output vector here. It's a queue, double-ended queue actually. Start creates threads.
What was the question there with is this necessary? On the right hand side, so
I had a comment maybe.
Yes.
Where is it?
In the enqueue, yes.
I think this is the bool. Okay, I have a bools. The finished one is written only once when all the threads should stop, but the ready one, I have a mutex for it, standard mutex. This signals the notify one from the for the summation consumer to take one result. Summation consumer. 1 second. I have a technical thing. 1 second. Okay. There should be a waiting mechanism. The main waiting and the one result. Get one. No, I need to go to this method, but today my keyboard is not good. get one DQ. Okay, finished.
The thing is, it's a classical application for the classical producer-consumer queue, or synchronized queue, or whatever you want to call it. You try to do something a bit different, which is fine. But I'm trying to understand what you are doing there. And especially why.
In this part that is on the screen.
I was thinking about the right-hand side and the existence of, if you scroll up a little bit, the right-hand side, you have two mutexes, the Q mutex and the ready mutex, and how do they interact with each other?
I haven't analyzed this.
Because what you are trying to do, if I understand correctly, is you have the Q mutex that protects only the mutex. And then you, after enqueuing something into the mutex, you set ready on true, and you notify a consumer, and the consumer will set ready on false, but I'm not sure where is it going to wait. Yes?
You said queue into the mutex, and that leaves me a bit confused. I queue into the result DR, and
yes, you enqueue into the queue, and you have a mutex that protects only that queue. But on the DQ side, I'm not sure where you check that the queue is not empty and how you do that. Or you do that in the caller of the DQ function. You wait for ready to become true.
The consumer waits. The summation consumer waits for the product consumer's queue to be empty, to be full or not empty.
But is this in the DQ function or is it in the caller of the DQ function?
It's in just this boolean.
Okay, and you lock. Could you scroll a bit to the right? The left window a bit to the right.
All right.
Because you have unique mutex, yes. Cond TM. Who is cond TM?
This is the.
It's a third mutex.
Yes, I have the unique lock inside the scope in order to use the conditional variable.
Because the idea is with the condition variable, with the mutex associated to the condition variable, that whoever changes the condition on which you are waiting in line 40 must not do so without taking the mutex. So normally, the producer should also take the mutex, update the ready variable that you are checking in line 40, notify the condition variable that you are waiting on in line 41, and then unlock the mutex so that they happen. Those two operations, those two pairs of operations happen each pair atomically. Otherwise, so you want to cover against the risk of the following sequence. You check the ready variable, it is false, so you decide you go to sleep, but before you actually call the sleep method, the producer sets the ready variable on true, sends the notification, and goes. That's why you would take the same const t mutex both in the producer and in the consumer. And that's the purpose of the mutex that you specify in the wait statement. The mutex there is released for the duration of the wait. So I guess the ready mutex is used only in the code on the right-hand side, and the other one only on the left-hand side.
Yes, they are distinct, it seems.
And that's not okay,
I see.
because now you have two mutexes for protecting the same variable. And this means the variable is not actually protected. Normally, you should have the same mutex for everything. So for the queue, for the condition variable, and in that case, the ready variable is not even necessary, because anyone can check if the queue is empty or not, the queue structure, I mean. You may need some other variables. I showed the example with a Boolean variable for signaling the end, the closure of the queue.
Right. Okay.
Okay. If you have some more questions, please ask. Otherwise, I propose that I'll come back to you a bit later.
Sure.
Okay.
Okay, I'm the next one.
Yes.
So I also have a lab 2.
Yes.
I have a simple class for vector. I just have a list of integers. And I have a producer, a consumer that communicate through a buffer. So here I have a put method where I acquire the lock. And while the queue is at max capacity, which usually is 1, but I wanted to try more stuff with it. We wait for the signal, and the signal is called when we add a value in the queue. And it's the same principle for the get method, which is used by the consumer. Same, we use a condition, we wait for a signal, and then we just, for the producer, we just put things in the queue. And for the consumer, we just get things from the queue and we add them to the result. So
okay, as a side note, if you have something like the queue size here,
yes.
Of course, it's a good idea to test with a queue size of 1, but most of the tests should go with a larger queue size.
Yes, so I tested with 1 to 5 because my vector is of size 5. I tested with every value. Let's
Put a larger vector,
another vector.
a larger vector.
Oh, well, yes.
Make it for simple test. Make it. I don't know. Well, for very simple test, it's okay to put a vector of size 5 and a Q size of 2 or 3.
Yeah.
But for serious, you will never be able to do serious checks on concurrent programs or on parallel programs, for that matter, with very small sizes.
Yes, I know.
So have larger tests as well.
Well, I can write one now.
A Q size of 1 is also a very special case in the sense that, well, it is a corner case that could trigger some bugs that are hiding otherwise, but it's also, from the other perspective, some behaviors that may happen on larger size Q will not happen on a Q of 1.
Yes,
not to mention that the performance is really bad for a Q of size 1.
Oh, well, of course. That's what I was testing, the worst performance that can be, because the Q size, the size of the vector, it's basically doing the products first and then just adding them. But yeah, it depends on the numbers as well, I think.
By the way, since we are here, let me tell a story from years ago. Do you know about a language called Prolog?
Yes.
Did you work in it, programming
we
it?
had last year a course in it.
Because years ago, as a student, the first things I had to do in Prolog were things like reversing lists. And, well, it's feasible, but not the thing Prolog was designed for. And then, well, in another context, I had to solve a problem, well, simplified one, but something like you had some family relationship described in a pseudo-natural language, like John is the son of the sister of whoever, and then to answer, the family relationships were given in Prolog, and then a question in pseudo-natural language was to be answered. And then I saw that in a few lines of code, I could solve this problem. And the conclusion was, well, it's useful for something, that language. It's indeed useful. It's not just an academic idea. And, well, more or less same for this parallel programming and stuff. If you are doing very small problems, then parallelizing them is a big effort, and the performance is usually even worse than the non-parallelized version. But if you have really large data, then you can see an improvement. Okay, back to...
Yeah, well, I don't think any of us ever used Prolog after the course.
At least there is a very popular puzzle. It's sometimes called Einstein's puzzle, with some houses and some relations between their occupants. Did you take this as a problem to be solved in Prolog?
Never
Yes.
thought about it.
Yes, we did.
Because that's one of the problems where it shines.
So many logical problems or problems that can be resumed to logical statements.
Yes. So we have that check against capacity. One more question regarding the code.
Sure.
So let's go back. Do you have a single condition variable?
Yes, I was single
That-
condition variable, and it's used for both put and get.
I guess you can create two of them.
One
Is
for
that
the put
correct?
and one for the get.
Yes. So
yeah,
one
I
for
think
signaling.
That's the best practice. Yes.
Sorry?
I think that's the best practice too. So
Yes, to have distinct condition variables for distinct conditions to be signaled, but not this way, not this way. So one for communicating from put to get and the other for the other way around. No, the declarations were good. They are in the same class. They are both on the same
put
mutex.
to get.
But one of them is to be notified in put and waited on in get, and the other will be notified in get and waited on in put.
I see.
Because one of them now, condition 2, I guess, signals that there's some element to be consumed, and the other one signals that there is an empty slot in the queue.
Yes.
Used. Let's see that it works correctly.
Yes.
Okay. Good. Good. So I think we close here. If you have any questions, please ask, and I will take the other ones for the labs. So thank you again, and see you next time. Bye.
Thank you. Bye.
Bye.